Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access a course page on my personal website, Arif.me. You can click the appropriate link under the lecture resource column over here and view this notebook in the NB viewer and run it online in Binder. You can always download the notebook from the course GitHub account Arif PUCIT, and all the notebooks for this course are housed in this public data science repository, data science. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for today's session. Lecture number 4.3 of the fourth module, Mathematics and Statistics, for the course titled Tools and Techniques for Data Science. Well, my dear students, we have covered two video sessions on mathematics and statistics for data science. Lecture 4.1 was on descriptive statistics and lecture 4.2 was on inferential statistics. Today's lecture 4.3 will cover the basics of linear algebra, and the next lecture 4.4 will cover relatively advanced concepts of linear algebra for machine learning. Well, linear algebra is a subfield of mathematics that deals with the vectors, matrices, solving systems of linear equations, and linear transformation. The singular value decomposition and eigen decomposition, they help in dimensionality reduction, ranking of web pages, designing recommender systems, topic modeling, semantic analysis, and so on. And this is what I will try to cover in two sessions of linear algebra for machine learning. And here is the agenda for today's session, which I have divided in further three sections. This section 1 deals with vectors and the different operations that we need to perform on this data structure. I will be covering all these concepts along with Python code to give you proof of concepts as we progress. Okay, so this section 2 deals with matrices, its types, and the different operations that we need to perform on this data structure. My dear students, if you already know these concepts or want to jump onto a specific topic, you can click the appropriate link in the table of contents in the description box below. And this section 3, this is a very comprehensive section on solving overdetermined and underdetermined system of linear equations, which can be consistent or inconsistent. And I will close this lecture by practically understanding the math involved behind simple least square and multiple least square methods to solve inconsistent overdetermined system of linear equations. And these sections 4, 5 and 6 will be covered in next lecture, that is 4.4, inshallah. My dear students, these are the libraries that you need to import. Pay specific attention to this plot underscore helper module that contains code for drawing the vectors and for linear transformation. Some of the codes of this notebook are adapted from these links. I'm particularly thankful to Dr. Cron for providing such marvelous resources on this subject. Okay, so let's start with the overview of vectors. My dear students, while studying the subjects of physics and mathematics at secondary school level, we have studied the terms scalars as well as vectors. A scalar is a quantity that has magnitude but no direction. And some examples of scalar quantities are length, speed, mass, area, volume, and so on. On the contrary, a vector is a quantity that has magnitude as well as direction. And some examples of vector quantities are displacement, velocity, weight, and force. In physics, we represent a vector as an arrow of specific length representing its magnitude and drawn at a specific angle representing its direction. In computer science, a vector is an ordered list of numbers as shown over here. And these numbers can be the price, area, and maybe the number of bedrooms a house has, or maybe the age, weight, and blood pressure of a person. In mathematics, vectors are generic objects that behave in a certain way when they are added or scaled. Well, vectors can be two-dimensional, three-dimensional, and so on to n-dimensional. The two and three-dimensional vectors are pretty easy to visualize. However, if we are able to understand the vector operations in two dimensions, we can map the concepts to the larger dimensions as well. So let me start with the mathematical and graphical representation of vectors in 2D space. Well, algebraically, a vector is represented using a lowercase alphabet having a comma separated list of numbers written horizontally or maybe from top to bottom like this. And another way of writing a 2D vector is a sum of scalar multiples of unit vectors. We will talk about unit vectors soon. For the time being, just remember this I hat is a unit vector in the direction of positive x-axis, while this j hat is a unit vector in the direction of positive y-axis. And let us understand this using the 2D Cartesian coordinate system as well, as shown in these three figures. Well, if you concentrate on this left figure, you can think of a vector as a point in space. Consider this vector represented by a green arrow, this point 2, 3, 2 units along the x-axis while 3 units along the positive y-axis. Graphically or geometrically, it is represented by a directed line segment whose length is the magnitude of the vector and the angle represents its direction. My dear students, a vector is normally visualized as a line segment that starts from the origin. In this left image over here, we have three two-dimensional vectors. This 2, 3, minus 3, 1, and this minus 1.5 and minus 2.5. All of these three vectors have their tails at the origin. If you see this vector in the middle diagram, its tail is not at origin, rather is at point 2, 2, and its head is at point 6, 8. To translate this vector so that it starts from origin, we translate it 2 units to the left and 2 units down. Note in this diagram, its head is now at 4, 6 instead of 6, 8. If you closely observe, both these vectors have same magnitude and same direction. Great. Okay, my dear friends, similar to vectors of rank or degree or order 2, we can have vectors of rank 3 as well, having 3 scalar values. Once again, algebraic representation of a rank 3 vector can be having 3 comma separated values written horizontally or maybe vertically as a vector matrix or a column matrix. Do note that a 3D vector can also be written as a sum of scalar multiples of its 3 unit vectors, where this I hat is the unit vector in the direction of positive x-axis, this j hat is a unit vector in the direction of positive y-axis, and this k hat is a unit vector in the direction of positive z-axis or z-axis. And let's understand this using this 3D Cartesian coordinate system as shown in this figure, represented by a cube. You can see this is the x-axis, this is the y-axis, and this is the new axis, the z-axis, and all these three axes are perpendicular to each other. This vector v is shown in bold red, having the three components A, B, and C along the x, y, and z axes respectively. My dear friends, if you have a clear understanding of vectors in 2D space, you can extend your understanding to vectors in 3D space and to 4D and maybe 5D space as well. Let's see the Python implementation. Let's start by visualizing a vector in 2D space having its head at location 3, 2 and the tail at origin. For this I am using this plot underscore vector function. These plot underscore helper module has been taken from Dr. Lorena Barbara, her workshop in SciPy 2019. This plot underscore helper.py script is containing a lot of functions like this plot vector and plot linear transformation as well. Let me run the code of this cell. Great, beautiful. So this plot vector function over here, this actually is using the matplotlib and numpy library functions to create this 2D Cartesian coordinate space with this vector having its head at point 3, 2 and its tail at origin 0, 0. Let me show you some more examples. In this example I am passing a complete list having 4 tuples, each representing a vector. Let me run it, shift enter. You see these are 4 different vectors. For example, this is vector 3, 3 in the first quadrant, and this is vector 3, minus 2 in the fourth quadrant. Let's see another example over here. And right now I am passing 2 arguments to this plot vector function. The vector v 4, 3 and its tail 2, 2. So you see this vector is now having its tail at point 2, 2 and the head is at point 6 and over here it is 5. Great. Fine, let me run the code of this example 4 as well. Over here I am drawing 3 different vectors, all having their tails at point 2, 2. Let me run this example code. Okay, so over here I am drawing 3 different vectors, all having their tails at different points. And consider this small vector having its tail at point 3, 2 over here. And this is the vector actually 1, 3. Therefore, you can note its head is currently at location 4, 5. I hope this makes sense. My dear friends, mostly we draw vectors with their tails at origin, and of course we can translate any vector to origin by subtracting the xy coordinates of its tail from the current head and tail coordinates. And this is what is shown over here. So all the 3 vectors starting from the origin. Okay, so now let me talk about the magnitude of a vector. And let's see how we can calculate the magnitude or norm of a 2D and 3D and so on to ND vector. Or in other words, computing the magnitude of a vector having 2, 3 and so on to n elements. And one way is of course by graphically drawing that vector in a coordinate system, and the other way is using these formulas. The most commonly used is the L2 norm, also known as Euclidean norm, which calculates the distance of the vector coordinate from the origin of the vector space. And the formula to calculate it is the square root of the sum of the squared values. Please do read about the squared L2 norm, L1 norm and max norm. And let me move on to this example code for a proof of concept. The problem statement is that we have a 2D vector having its head at point 2, 8 and tail at point minus 2, 2. and we need to calculate its magnitude. Before I execute the code of the cell, let's review the code. These first 3 lines, they are actually translating the vector to the origin. So you see I am subtracting this vector 2, 8, and I am subtracting this tail value from the head value, so that I get the vector actually 4, 6. Please do the math. Over here I am actually using the plot vector function to plot the vector, and then over here I am calculating the L1 norm first. Well, to calculate the L1 norm, you can use this norm method of the linear algebra module of numpy and pass it the vector v, and the second argument ORD equals 1 means that we need to calculate the L1 norm. If I use the norm method and pass ORD is equal to 2, that means I am calculating the L2 norm. And of course you can use the mathematical formula to compute it, and similarly we can compute the scared L2 norm and the max norm. Let me run it. So this is what it is. This was actually the vector 4, 6 having its tail at point minus 2, 2, and I have moved it to region first, and then I have calculated its L1 norm, L2 norm, scared L2 norm and max norm. Remember my dear students, most of the time we will be using the L2 norm or the Euclid norm. My dear students, please, this is the time to pause this video for a while and do the mapping of the code with the output. And let me move ahead. Okay. So after understanding the magnitude of a vector, now it is time to see how we can calculate the direction of a vector. Well, the direction of a vector v is the measure of the angle that it makes with the horizontal axis in the plane. The two units of measurement of angles are degrees and radians. As you all know that a complete circle is divided into 360 equal degrees. Each degree can be further divided into 60 equal parts called minutes, and each minute can be further divided into 60 equal parts called seconds. The other measure of an angle is radians, and 1 radian is the angle made at the center of a circle by an arc whose length is equal to the radius of the circle. And since the circumference of a circle is 2 pi, therefore 2 pi radians equals 360 degrees. This is just a recap. I'm sure you all have studied all this in detail in your secondary school. And there are 2 ways to measure the direction of a vector. One is geometrically or visually, and the other is mathematically using this inverse tangent formula. My dear students, the most common way to measure the angle visually is to measure the angle counterclockwise, like over here. You move counterclockwise starting from the positive x-axis. So this is the angle of 50. While in this figure over here, the vector is making an angle of 200 degrees starting from the positive axis counterclockwise. While over here, if you see in this figure, the angle is 30 degree. So this angle of 30 degree is measured from the negative x-axis in clockwise direction. Such a measured angle is represented with a negative sign. I will describe this with an example in a bit of time. My dear students, you can mathematically compute the direction of a vector using this inverse tangent formula. Theta is equal to tangent inverse y over x. And we know, of course, the x and y, the components of a vector. And the point to remember over here is that the inverse tangent formula returns the angle in radians and gives the shortest angle from either positive or negative axis in either clockwise or anti-clockwise direction. Let me describe this is using a sample Python code so that you can understand what I'm saying. Let's see this example, example 1. Suppose we want to find the direction of a vector with coordinates 4, 6. Let me execute the code of the cell to visually show you the vector first. Okay, so here it is. So this is the vector having its head at point 4, 6 and tail at origin. To mathematically calculate the angle, I have used the A10 method of the math module, and I have passed it the ratio y over x, the y component divided by x component. The arc10 method returns the angle in radians, which I have converted into degrees by multiplying it by this 180 over pi. So this pi is a constant, so I have used math.pi. And you see this comes out to be 56 degree. And if you visually see this, it is quite similar. My dear friends, remember this point. Since this vector is in the first quadrant, so the angle returned by this arc tan is computed from the positive x-axis in the counterclockwise direction. So that's why it is positive. However, in this case, in this example, this will be a bit different. You see, this time the arctan method will return this angle from the negative x-axis, because this is the shortest angle, and that is 56 degrees. So we need to actually convert it, because we are used to of calculating the angle from the positive x-axis in the counterclockwise direction, while over here the arctan method is returning me the shortest angle from the x-axis, and that is minus 56. So to convert it, I have to add 180 degrees to this. So this is 123. I hope this math is making sense to you. Let me move on to the third example. And over here, this time the vector is in the third quadrant. So the shortest angle is 56 degrees. You see, from the negative x-axis, this is 56 degrees. And we need to add 180 degrees, because we are used to of computing the angle from the positive x-axis. So over here again, I have added 180 degrees. And finally over here, this is the vector in the fourth quadrant. So the angle returned to me this time by the arctan is measured from, of course, the positive x-axis, but in the clockwise direction. So this, in the clockwise direction, this angle is minus 56. And of course, I'm used to of calculating the angle from the positive x-axis in the counterclockwise direction. So I have to add 360 degrees to this, so that I can get 303 degrees. My dear students, please do the math. You should have a very clear understanding of this thing, that the arctan method of the math module returns the angle in radians, which we need to convert into degrees, and then we need to ensure that that this arctan method is returning us the shortest angle from the x-axis, and we need to check out whether we need to make some addition or subtraction to this angle. Great. So let's now talk about the components of a vector. My dear students, now we have a fair idea about the magnitude as well as the direction of a vector. Let us talk about the components of a vector, and let us start with the 2D vector. Consider this force having a magnitude of 10 newtons applied at an angle of 30 degrees along the positive x-axis or the horizontal axis. And in this figure, the x component of the vector f is fx, shown as w over here, which is 5 units along the positive x-axis, while the y component of the force F is Fy, shown V over here, which is 2 units along the positive y-axis. And since this is a right angled triangle, therefore applying Pythagoras theorem, we can compute the Fx component, that is F cos theta, and the Fy component is F sin theta. And let us do this practically using a simple Python code as shown over here. If you see the first 4 lines, these 4 lines are computing the x and y components of vectors having a magnitude of 10 and making an angle of 30 degrees. So fx is equal to f cos theta and fy is equal to f sin theta. Remember this sine and cos are taking the input angle in radians. So I have to convert degrees to radian. Great. Then over here I am just calculating the magnitude again for verification using the norm method. Let me run this code. And of course I have used the plot vector method to plot it as well. You can see this is the vector. The fx is 8.66 Newton, fy component is 5, the magnitude is again 10 and the angle is 30 degrees. So you have given me the force 10 Newton and angle 30 degrees, and I have computed the fx and fy components, and later from the fx and fy components I have once again verified it by computing the L2 norm and the angle. So which is the same. Great. So this is another example in which we are calculating the xy components of a 2D vector given its magnitude and direction. So let me execute it. My dear friends, please do make time, stop the video, understand the math, use the calculator if you want to, use the paper pencil, and then move ahead. Okay, let me talk about the components of vector in 3D space, x, y, and z component of a 3D vector. In this figure, consider this vector f in 3D space. My difference, the x, y, and z components are all perpendicular to each other, as I have said before as well. Try to visualize this z axis is coming out of the screen towards you. And this vector f is making an angle theta x with the x-axis, theta y with the y-axis, and theta z with the z-axis. Do try to visualize the three right angled triangles in this figure. And one easy way of doing it, that if you are sitting in a room, just look at one of the corners of your room where the two walls of your room are meeting with the floor, thus making the three axes or lines, one moving left, the other moving right along the floor, while the third one is moving up towards the ceiling. Okay, so I have created this example for your understanding. Let's say that the magnitude of a vector is 8.2463 and it is making an angle of roughly 60, 43 and 60 degrees with the x, y and z axis respectively. Let me run the code of this cell. Great. So you see the x, y and z components of this vector are 4, 6 and 4 respectively. So you can write it as 4i plus 6j plus 4k, where I, j, k are the unit vectors. And of course I will talk about the unit vectors soon in detail. For the timing, let me move ahead and talk about two fundamental vector operations that are addition and scaling. And let's talk about the vector addition first. My dear students, two vectors of equal length can be added together to create a new vector. And this can be done graphically as shown in this figure over here using the head to tail rule. If you see, you draw the first vector A with its tail at the origin, and then you draw the second vector b with its tail at the head of the first vector, and the resultant vectors is a plus b, which is drawn such that it connects the tail of this vector a with the head of this vector b. And mathematically it is very simple. You just add the corresponding elements of the two vectors. If the vectors a and b has the three vectors, so you add the first element of a with the first element of b second element of A with the second element of P, and the third element of A with the third element of P, and you get the resultant vector. Let us practically see this using Python code. Over here, there is nothing new in the code. Let me just simply execute it. So you see, we have added the two vectors U and V to get the resultant vector R. This is also shown graphically over here. So you see mathematically this U is 6 minus 1, V is minus 3, 4, and you just sum it up, you get 3, 3. So this is the vector 6 minus 1, this is the vector graphically, and this is a minus 3, 4 drawn at the head of the first vector U, and this is the resultant vector R, 3, 3 graphically. I hope this makes sense to you all. And finally, the magnitude of R is calculated and the angle as well, which we have done before as well. Anyway, so this is another example just for your practice. I have made a lot of examples so that you can understand things easily. Please do review the code. Okay, so let's move on to the scaling part. My dear students, after addition, the second fundamental operation that we perform on vectors is scaling, and that is multiplying a vector with a scalar value which can change the magnitude of a vector and can reverse the direction of the vector as well if the scalar value is negative. And note in this example, we are multiplying a vector minus 4 minus 6 with a scalar value of minus 0.5, and the resultant vector is 2, 3, having half the magnitude and opposite direction, and shown in red color in this figure as well. And here is the Python code that do this job. Simple to understand. If you are following this video from the very beginning, let me run it. So this is the vector, original vector, and this is the vector in reverse direction. You see I have computed the magnitude of the vector as well, and of course the angle as well. So the code is very well commented, and if you are following this video from the very beginning, this will be a piece of cake for you. And over here I have done another example in which there is a vector 1, 1. I have tried to scale it with the value of 3. So this time the angle will remain the same, 45 degrees. However, the magnitude has changed. Great. Okay, so now let's talk about the unit vectors. My dear students, the concept of unit vectors, basis vectors, their linear combination and span, they are heavily used in vector calculus and linear algebra. Let us talk about the unit vector first. Every vector has a corresponding unit vector, which points in the same direction but has a magnitude of 1. It is represented by a hat sign over the alphabet and is computed by dividing the vector components by its L2 norm. As a sample code, you can see over here a vector in 2D space is shown. Let me execute the code. Okay. See this graphical representation of this vector 3, 2. This is a vector 3, 2. Having a magnitude of 3.6 as calculated over here using the L2 norm, and its corresponding unit vector, which is 0.832 and 0.55, and which is graphically represented over here. So this is the unit vector which I have computed using this formula by dividing the magnitude. Okay, and note the direction is same. Let's repeat this for a 3-dimensional vector. I have calculated the unit vector of this 3D vector 12, 3 minus 4, having a magnitude of 13. So I have divided it once again. I have divided the x component with the magnitude I have divided the y component, that is 3, with the magnitude, and I have divided the z component with the magnitude, and this is a unit vector. Great. So after the unit vector, let's talk about the basis vector. My dear friends, basis vectors are special unit vectors pointing along the x or the y axis. In two-dimensional space, I hat is the basis vector having a magnitude of 1 and pointing towards the positive x-axis. And similarly, this j hat is the basis vector having a magnitude of 1 and pointing towards the positive y-axis. And similarly, we have the I, j, and k in case of three-dimensional space. And of course, a vector can be represented as a linear combination of these basis vectors. And let me visualize this using this Python code. Okay, so great. So this is a vector 3, 2. This is the vector 3, 2. So the x component of this vector I hat 0, 1, and this j hat over here, this up till here. And note that the vector this I have created using the linear combination of the basis vector, that is 3i plus 2j. So this is I hat. I have scaled it with a value of 3. I got 3i. And this is j hat, and I have scaled it with 2. So this is 2j. So this is 2j, this is 3i, and this is the vector v, that is 3, 2. So the main point is, my dear students, that any vector in space, like for example 3, 2, can be written as a scaled version of the basis vectors. And the basis vectors I is a vector along the positive x-axis having a magnitude of 1. And this vector j is a basis vector in the direction of positive y-axis having the magnitude of 1. And we multiply these basis vectors with a scalar value, and we add them up to get the vector. And this is what is shown over here in this Python code. I hope this makes sense. So after the unit vector and the basis vector, let me talk about the linear combination and the span. Okay, so the concept of spanning the vector space actually is spanning is a set of all possible linear combination that we can create from basis vectors. Let me straight away show you this code. We have two basis vectors I and j. I is 1, 0 and j is 0, 1. See this loop over here. In this loop I am generating let me generate just 100 first. I'm just generating 100 different vectors from these two unit vectors. The scale values m and n are randomly generated from -8 to +8 using this rand-int method of random module of NumPy library. Let me just execute and plot it. Yeah, great. So you see, these are the 100 different vectors that are generated from the basis vectors. Let me increase this 100 to 1000 and let me execute it again. You see, so you can say that the span of the basis vectors I and j is this whole 2D space. By that I mean, if I keep on increasing these values, I can cover the entire space from this. So this is what the concept of spanning is. And of course, this example is not limited only to the basis vectors 1, 0 and 0, 1. Over here I have two different vectors, -2, 1 and 1, -3, and I have repeated the same code and I have generated the span of these vectors. Okay, so let me further elaborate by this example over here. In this example, I'm trying to generate these 50 random vectors from linear combination of two vectors -2, -1 and 1, 0.5, and rest the code is same. Let me execute it. Oops, what has happened? Actually, in this example, these two vectors C and D, these two vectors C and D are collinear, that is scaled version of each other. Uh, uh, you can get this vector D by multiplying vector C with a scalar value of -0.5. So if you divide this -2 with -2, you can get 1, and if you can divide this -1 with -2, you get 0.5. So they are actually uh, dependent. We say that these two vectors C and D are not linearly independent or linearly dependent, and therefore you see a very straight line over here. So in short, let me say that since these two vectors C and D, they are linearly dependent, therefore their combinations are not able to travel all over the plane. My dear students, I will like you to keep this point in mind, the concept of linearly independent and linearly dependent vectors, as we will be using this while solving the system of linear equations in section 3 of this session. Let me move ahead, and let me talk about now the vector to vector multiplication. Well, my dear students, we have seen how to add two vectors. Now let's see uh, the two ways to multiply two vectors: the dot product and the cross product. And remember, the output of a dot product is a scalar value, while the output of a cross product is a vector. And mathematically, you can compute the dot product of two vectors of same size by the summation of the product of their respective components. And geometrically, you can compute the dot product of two vectors by multiplying the magnitude of the two vectors and the cosine of the angle between them, as shown in this formula. The formula for to compute the angle between two vectors is shown over here: cos inverse u dot v over u magnitude divided by v magnitude. And remember, this vector dot product is commutative in nature and is used in determining orthogonality, vector projections, vector decompositions, and in neural networks as well. Let me move on to an example which says that we have two vectors, 2, 2, -1 and 5, -3, 2. And what we need to do is we need to compute the dot product of these two vectors, and we also need to find the angle between them. And once again, I have written these two formulas. You can find the dot product using this if you don't just know the components, and if you know the angle, you can use this formula. And this is what I have done over here in this piece of code. So these are the two vectors, these are the magnitudes, and I have computed the dot product. My dear students, if you see the code once again, this norm method is the method of linear algebra of the NumPy module, and I've passed over d is equal to 2. That means L2 norm. And over here I am using the dot product using the dot method of the NumPy library, and I have passed it the two vectors. You can calculate the dot product using this function of NumPy, or you can simply just multiply it as you know the formula. And similarly, to compute the angle, I have used this. I hope this makes sense. So let me move on to another example. So this is another example. Once again, these are the two vectors given as the basis vectors: 2i plus 2j plus 3k, 6i plus 3j plus 1k. So if you just know the components, you can use this formula. And if you know the angle, you can use this formula. It's just a repetition. My dear students, please, I strongly recommend that if you're not comfortable with all this, you have forgotten what you have done in your secondary school courses of linear algebra or math. Please do the math on using the paper and pencil for a clear understanding. And let's talk about the vector cross product now. Unlike dot product, the cross product of two vectors produce a new vector, and the direction of the resultant vector is given by the right hand rule. Well, if the components of the two vectors are known, you can determine their cross product using the matrix determinant as shown over here. I will talk about the determinants soon when we'll be talking about the matrices in the next section. For the time being, just remember that over here we have computed the determinant of this. If the magnitude of the two vectors and the angle between them is known, you can determine the cross product by multiplying the two magnitudes and the sign of the angle between them. And this n hat is actually the unit vector in the direction given by the right hand rule again. And the formula to compute the angle between two vectors is using the cross product is shown over here. Remember, unlike a dot product, cross product is not commutative. A cross B is not equal to B cross A. And of course, here is an example as usual as for our proof of concept. Over here, instead of the dot, I have used the cross method of the NumPy library to compute the cross product. The code is quite similar to the previous example. Let me straight away run it. So this is these are the two vectors and their cross product, and here is the angle. I have also computed the angle. Great. Fine, let me move ahead and let me talk about now the orthogonal and orthonormal vectors. My difference, two vectors having an angle of 90 degree between them are orthogonal to each other. And similarly, a vector that is perpendicular to a surface as shown over here is called orthogonal. And there are two ways to determine if two vectors are orthogonal or are perpendicular to each other. And the first one is their dot product will be 0, and another is their cross product is equal to the product of the magnitude of the two vectors, because sine of 90 is 1 in this case and cos of 90 is 0. Another related term is orthonormal vectors, which are special orthogonal vectors having a magnitude of 1. So the basis vectors are an example of orthonormal vectors. And here is the proof of concept. Once again, same piece of code. Let me just run it. You see, the angle between the two vectors is 90 degree as shown over here. And their dot product is 0 and their cross product is equal to the product of the magnitude of A and B. Please do the math. Okay, so my dear students, we are done with section 1. That was a very quick recap, but a comprehensive recap. I've tried to give you a hands-on overview of vectors in linear algebra. We have seen the mathematical and graphical representation of vectors in 2D and 3D space. We have seen as to how we can compute the magnitude, direction, and components of vectors. We have covered the addition and the multiplication of two vectors, both the dot product as well as the cross product. We have understood the unit, the basis vector, their linear combinations, and the span of the basis vectors in the entire 2D space. My dear students, if you are not comfortable with these concepts, I strongly recommend that you should watch and practice section 1 related with the vectors before we move on to this section 2, which gives a comprehensive overview of matrices. And to start this, let me start by saying what Morpheus has said in one of my favorite movies, Matrix, and that is, unfortunately, no one can be told what the matrix is. You have to see it yourself. Okay, so let's move ahead with this part and start with the overview of a matrix. Well, a matrix is a two-dimensional array of scalar values, and this is how we will represent a matrix having m rows and n columns. You see 1, 2, 3, 4, so on to m rows are there, and 1, 2, 3, 4, so on to n columns are there. And let me talk about the matrices and its types. And before I talk about different operations that can be performed on matrix, we need to describe the type of matrix, and this is a very basic way of creating a matrix in NumPy. You use the np.array method and pass it the vectors. Over here I have created a 3 by 3 matrix, named it A, and this ndim, shape and size, these are the attributes showing the dimensions, the shape and the size or the number of elements in this matrix. Okay, so let's start with the different types of matrices, and we all have seen the row vectors, my dear friends, which is a matrix with one row and one or many columns. And this is a sample code that creates a row vector. Let me run it. This creates a row vector and takes its transpose as well, which doesn't affect the row vector. So this is a transpose. This dot t is actually taking the transpose. And let's talk about the column vector. This is a sample code that creates a column vector, actually a 2D matrix with exactly one column and one or many rows. I'm sure you are comfortable with this. The point to observe over here is that the row vector is one dimensional, while this column vector is two dimensional. And that is the reason that when we take the transpose of a column vector, we again get a 2D array, but this time having one row and three columns. You see? Okay, so zero matrix, a matrix having all its elements as zero is a zero matrix. We can use NumPy zeros method to create a zero matrix of specified number of rows and columns and of a specific data type as well. Ones matrix. Similarly, we can use the NumPy ones method to create a matrix having all its elements as 1. You specify the number of rows and columns. Random integer matrix, you can use the rand_int method of the random module of NumPy to create a matrix of size, let's suppose over here 5:3, and including elements from 0 inclusive to 10 not inclusive. Let me run it. Let me run this code again and again and again. I hope this makes sense. You are getting a randomized matrix of 5 rows and 3 columns, and the elements of this matrix are from 0 to 10, where 10 is not inclusive. Great. Right, then we have square matrix. And of course we can create a square matrix once again using the rand_int method. You pass it the size 3, so it is a square matrix. A matrix having same number of rows and columns. Over here I'm using the seed method to ensure that no matter how many times I execute this code, it will generate the same matrix. Let me run it again and again. So no matter how many times I run it, I get the same matrix. So this is because I'm using this seed method and passing it the same value. Anyway, symmetric matrix. Symmetric matrix is a square matrix in which the top right triangle is the same as the bottom left triangle. So if you see this matrix, the top right triangle 1, 7, 5, these are the three values above this triangle, and these are the same values over here below this triangle. So these are same. You can also note another important property of a symmetric matrix over here is that its transpose is equal to the matrix itself. So if you take the transpose of this matrix, it will be the same. So let me do this using this code. So this is the matrix A. So you can use the transpose method. You can use this transpose method. You can just use the this transpose dot t attributes of the matrix. You can, this is more commonly used. However, if you are more comfortable with this, you can do that. Okay, so after the symmetric matrix, let me talk about the triangular matrix as well. Given a matrix A having m rows and n columns, the upper triangular matrix of A has values only above the main diagonal, while the remaining elements are all 0. So this is upper triangular matrix. Let me say it again. The upper triangular matrix of this matrix A will have uh, only the values above the main diagonal. The values below the main diagonal are 0. And similarly, the lower triangular matrix of this matrix A will have 0 values in the upper triangle. In NumPy, if you want to do this, you want to create a lower triangular matrix of A, you use this method np dot tril, triangular matrix low, and for upper triangular matrix you use this. Let me run this code. So this is our matrix A, and this is the lower triangular matrix in which you see only the data below the main diagonal is there, and this is the upper triangular matrix in which only the data above the main diagonal is there, and rest of the elements are 0. Great. So then we have the diagonal matrix. A diagonal matrix is normally a square matrix in which all the entries that are not on the main diagonal are 0. So we have just the entries in the main diagonal, rest everything is 0. And let me execute this code as a proof of concept. So this is a matrix A. You have created a 4x4 matrix A using the rand int method as shown over here. We can extract the main diagonal of matrix A by passing matrix A to the NumPy diagonal method or DIAG method. So this will just extract the diagonal elements, that is 6, 9, 5 and 1. Similarly, if you have the diagonal vector, you can reconstruct the diagonal matrix by passing the diagonal vector to this diagonal method, and this is what is shown over here. Great. I hope this makes sense. So that means there are two ways to store a diagonal matrix, as a full matrix or a simple vector. So if you have a diagonal matrix, you can store it like this, or you can store it as just the diagonal. Great. Next we have the identity matrix, my dear friends. Identity matrix represented by I with a subscript n representing the size. So it is always a square matrix having the diagonal elements as 1 and the rest of the elements are 0. And there are very important properties of identity matrix. And the first important property is that the vector of length n remains unchanged when multiplied by a matrix. Let me give you proof of these concepts. So this is an identity matrix of size 4x4, and if you want to create an identity matrix having the ones not on the main diagonal, you want them one position up, so you pass this one over here, the third argument, and if you pass this as -1, you get an identity matrix in which the main diagonal does not contain 1, rather the diagonal below the main diagonal contains 1. Please do go through with the properties of identity matrix. So if you multiply a matrix with its corresponding identity matrix, you get the same matrix. And if you multiply a matrix with its inverse, you get the identity matrix, and so on. Great. So let's talk about the scalar matrix now. Scalar matrix is a type of square matrix in which its principal diagonal elements are all equal and off diagonal elements are all 0. So in this case, we don't have ones over here, rather we have same elements. Great. Finally, we have orthogonal matrix. People call it the queen matrix as well, and that is why it is represented with a Q. It is a type of square matrix whose column vectors and row vectors are orthonormal vectors, that is, mutually perpendicular to each other and have a magnitude of 1. And these are some of the important properties of orthogonal matrix. If you take the product of two orthogonal matrices, you get another orthogonal matrix, and the transpose of orthogonal matrix will also be a orthogonal matrix. And when an orthogonal matrix is multiplied with its transpose, it will return an identity matrix, and so on. So they are extensively used in linear transformation, reflection, and permutation. Let me just run this code. So this is just a proof of concept, some of the concepts mentioned over here, some of the properties. So please do the math. Okay, so let me move on to the matrix operations. We know now a bit of different types of matrices. Let's see what are the different operations that we can perform on our matrix. First of all, matrix addition. Two matrices can be added if their order is same. That is, if this is a m by n matrix, so this also has to be a m by n matrix. Same number of rows, same number of columns. Only then they can be added. And this is just a proof of concept, a Python code. So please do the math. So after matrix addition, we have matrix-scalar multiplication. A matrix can be multiplied with a scalar value, and this code is a proof of concept for that. So this is a matrix A. I have multiplied it with a scalar value B, which is 2. Great. Then is the matrix Hadamard product, matrix multiplication. There are basically two ways to multiply two matrices. One is this Hadamard product, and the other is dot product. And let me talk about the Hadamard product first. Well, for Hadamard product, the two matrices must be of the same size, as it is element-wise matrix multiplication. And mathematically, Hadamard product is represented by a circle with a dot in between. And this code over here is a proof of concept which creates and then perform element-wise multiplication of two matrices of same order. See, the size is same. So these are the two matrices, matrix A and B, and this is the Hadamard product of these two matrices, element by element multiplication. And for Hadamard product, you use this symbol, asterisk operator, in Python. Let's talk about the matrix dot product. My dear friends, when we say matrix multiplication, we actually means matrix dot product. And in order to perform a dot product on two matrices, the number of columns of first matrix must equal the number of rows in the second matrix, and the resultant matrix will have number of rows equal to that of the first matrix and number of columns equal to that of the second matrix. And this is what is shown over here. And note the technique of multiplication. Suppose that we want to multiply this matrix A, which is a 3 by 2 matrix, with this matrix B, which is a 2 by 2 matrix. First row is multiplied with the elements of the first column. So this is this value. Then the first row is multiplied with the element of this second column, which is this value, and so on. So we have done this many a times in our secondary school. Just see the code. So this is the dot method that is used to multiply two matrices. You can use this at the rate symbol as well. So this at the rate symbol is also doing the same task. But this is available only in Python version 3.5 onward. Okay, so matrix vector multiplication now. My dear friends, a matrix can be multiplied with a vector if the number of columns of the matrix equal to the number of elements in the vector. and the result is always a vector having the number of elements equal to the number of rows of the matrix, and this is what's shown over here. And see this code as a proof of concept. The numbering dot method or this at symbol, these can be used for matrix vector multiplication. I hope this makes sense. My dear friends, once again, if you are not comfortable with these matrix operations, please make time and practice doing all these operations using paper pencil, and confirm your results by running this Python code. Create different matrices, generate the result, and verify by doing it using paper pencil. This is important as we will be heavily using these operations in our upcoming sections of linear transformation, solving system of linear equations, and different matrix decomposition techniques. Let me move on to the next concept, and that is Frobenius norm. My dear students, we have talked about the norms of vectors, which are functions that allow us to quantify the magnitude of vectors. The most common vector norm that is used in machine learning is L2 norm, that calculates the Euclidean distance from origin. And this Frobenius norm of a matrix is the sum of the magnitude of all vectors in a matrix. And to calculate Frobenius norm, you just scale every element of a matrix, sum them, and take the square root. And in Python, if you want to calculate Frobenius norm of a matrix, you can once again use the same friendly norm method of linear algebra of the NumPy library and pass it ORD equals none, which is the default, of course. So please do the math. And let me move on to the transpose of a matrix. We have seen vector transpose. The matrix transpose is a similar operation which creates a new matrix with number of columns and rows flipped. This is shown over here. Well, transpose operation has no effect on symmetric matrix. And in Python, you can create a transpose of a matrix by using the T attribute of that matrix, or by using the transpose method of NumPy. I hope this is piece of cake. Anyway, then let me move ahead and talk about determinant of a matrix now. Well, my dear students, the determinant can be thought of as a function whose input is a scalar matrix and output is a scalar value. The determinant of a matrix is used to compute the inverse of a matrix. And if the determinant of a matrix is 0, that means it is a singular matrix, is non-invertible, having linearly dependent columns. Moreover, determinant is used in solving linear equations. And it also captures the notion of how linear transformation change area or volume. We have seen at secondary school level as how we can calculate the determinant of a matrix, and the process is described over here. In Python, you can calculate the determinant of a matrix using the DET method over here, this DET method. Let me describe this a little bit. Over here, the determinant of a 2 by 2 matrix is very simple. You just multiply A, D, and then multiply B, C and subtract them. And to calculate the determinant of a 3 by 3 matrix, what you do is you take this A and this 2 by 2 matrix. You calculate the determinant of this 2 by 2 matrix, ignore this row and this column. Then you take this B and ignore this column and this row, and DE, DF and GI. This is the submatrix. And then you have this. And of course, this is shown over here. You can easily calculate it. I've ignored this minus sign before this B and a plus sign before this C. So you just don't forget this. And you can compute this using this Python code, using this DET method of the linear algebra module of NumPy library. So this is the matrix A, and this is the determinant of matrix A, a 2 by 2 matrix, and this is matrix B, 3 by 3, and this is the determinant. Please check out using paper and pencil whether this answer is correct or not. Okay, so let me run this code and see what happens. And this is matrix A, matrix B, and you see this time the determinant is 0. Okay, so let me describe this. In this sample code, my dear students, you see the determinant of all these three matrices A, B, and C are 0. That means they are singular matrices or are non-invertible. If you observe this matrix A, the first column, that is 6, 4, is a multiple of second column, that is minus 3, minus 2. That is, you can multiply the second column by minus 2 to get the first column. Later we will see that such a matrix of coefficients represent two parallel lines, and it will be impossible to solve such a matrix for unknowns. Similarly, this matrix B and C also have dependent columns. I think enough about determinants. Let me move ahead and understand the inverse of a matrix. Well, my dear friends, the way numbers have reciprocals, and when we multiply a number by its reciprocal, we get a 1. Similarly, matrices have inverse, and when we multiply a matrix with its inverse, we get the identity matrix. And the inverse of a matrix is used to find the solution of linear equations, which we will see in our next section. My dear students, remember a matrix. For a matrix to have an inverse, it has to satisfy two conditions. First is the matrix has to be a square matrix, for example, a 2 by 2 or 3 by 3 or 4 by 4 matrix. And the next is the determinant of the matrix must be non-zero. So almost all of us know the shortcut way to calculate the inverse of a 2 by 2 matrix, which is something like this. We have the matrix A, we find the determinant of A, then we interchange the main diagonal, that is this A and this D, these are swapped, and we negate the remaining two elements, that is this B and C, they are negated. And then we of course divide every element of this matrix with the determinant of A, and this is how we calculate the inverse of a matrix. And the formal steps, if I write down the formal steps to compute the inverse of a matrix, they are: in step 1 we find the matrix of minors for the given matrix. In step 2 we turn that matrix into the matrix of cofactors. Then we find the adjugate or disjoint of that matrix. And then finally in step 4 we divide the adjugate matrix by determinant of the given matrix. Excuse me. So let me do this step by step over here. Let's suppose that this is a 3 by 3 matrix having these values, and we want to calculate the inverse of this 3 by 3 matrix. The first step is find the matrix of minors of this matrix. So for each element of this matrix, we ignore the values of the current row and column and calculate the determinant of the remaining values. And we put those determinants into a matrix, and you get the matrix of minors as shown over here. For example, for this 3, ignore this column and this row. We have this matrix of minor 0, minus 2, 1, 1. You compute the determinant of this. 0 into 1 is 0, 1 into minus 2 is minus 2. So 0 minus minus 2 is plus 2. So we have a plus 2 over here. Let me repeat it for this minus 10. Okay, so this one. So for this location, you ignore this row and you ignore this column, and you get the matrix of minor as 3, 2, 2, minus 2. And to calculate the determinant, 3 to the 6, that is minus 6, and 2 to the 4. So minus 6 minus 4 is minus 10. So we have minus 10 over here. So my dear students, this is the most computationally expensive operation. That is, given a matrix A, you need to find the matrix of minor of this matrix, and this is computed over here. After you have the matrix of minor, you turn this matrix into the matrix of cofactors. So you see, I have converted this matrix into a matrix of cofactor. And how we can do that? We multiply each element of matrix of minor with alternate plus and minus 1. So we multiply this with plus 1, this with minus 1, and this with plus 1. So we get this. And then again, we multiply this with minus 1, this with plus 1, and this with minus 1, and we get this. So we get a matrix of cofactors. And then we find the adjoint of the matrix. So to find the adjoint of the matrix, you take the transpose of matrix of cofactors. So 2 minus 2, 2. So this row has become this column. The second row has become second column, and the third row has become this column. And then we divide this adjugate matrix by the determinant. You find the determinant of this matrix, which is 10, and you divide each element of this matrix with 10, and you get this. So this is how we calculate the inverse of our 3 by 3 matrix. And you can think of the paperwork you need to do to calculate the inverse of our 4 by 4 matrix. And to our rescue, this inverse method of linear algebra module of NumPy is there. So a piece of cake. Great. You see, this is the same matrix which I have used over here. This is the same matrix, and it has given me the same result. So this is 0.2, minus 0.2, and 0.2, and over here we have 0, 1, 0, and so on. And one important property of matrix inverse is that if you multiply a matrix with its inverse, you get the identity matrix. Great. So the next topic is the trace of a matrix. The trace of a matrix is sum of all the diagonal entries of a matrix. Let me just run this code and show you this. So the diagonal elements, sum of the diagonal elements, 15. And these are some of the properties of the trace of a matrix. And this is a proof of concept for that. So that means if you have the trace of a matrix A or the trace of a transpose of that matrix, they are same, because the transpose doesn't have any effect on the diagonal elements. Anyway, so finally the rank of a matrix, my dear friends, the maximum number of linearly independent columns or rows of a matrix is called its rank. Let me repeat again. The maximum number of linearly independent columns of a matrix is called its rank. And two columns are linearly dependent if you can add or scale one column to make the other. So let me simply run this code and describe this concept to you. So the rank of a matrix having 0 element is 0, of course. This is a matrix of 3 elements just. Rank of 1. This is a matrix, a 2 by 3 matrix having a rank of 2. And over here we have rank of 3. And over here again we have rank of 2. So the rank of a m by n matrix is less than equal to the minimum number of its rows and columns. So what is the minimum of what is the minimum over here is 2, and what is the minimum over here is 3, and over here is 2, and so on. So I hope this rank is clear to you, and its application is of course finding the linearly dependent or the independent columns. And this is what is shown over here. So if you see this matrix A having this 1, 2, 3, 3, 6, 9, and 2, 4, 6, these 3 columns, so it appears that its rank should be 3, but its rank is 1. And the reason is that all the columns are linearly dependent on each other. and this second column can be achieved by multiplying the first column by, let's suppose, uh, by adding these two columns, we get this column. 1 plus 2 is 3, and 1 and 3 4 2, 2 and 6 4, 3 and 9 6. Great. And over here as well, as far as this B is concerned, the first and the second column are independent, but the third column can be achieved by adding the first two columns. If I add 1 and 0, I get 1. I add 2 and 2, we get 4. 3 and 2, we get 5. So over here we have the rank is 2 because we have two independent columns. And over here, since we have a single independent column, so we have a rank of 1. So this is what the application of rank is, rank of a matrix. Okay, my dear friends, that is all for section 2. So let's start with section 3. Section 3 of linear algebra. Well, in the previous two sections, I have tried to give a detailed overview on the types of vectors and matrices and the different operations that we can perform on these two important data structures. All this has been done with hands-on Python code, and keeping in mind that we are going to use this in the machine learning part of the course. Well, this section deals with one of the most important tasks of machine learning, and that is solving system of linear equations. And we'll start from very basic, and we'll end this session by solving linear regression equations using least squares method. If you are interested to watch or learn a specific subtopic, you can straight away jump to that by clicking the subtopic in the table of contents in the description box below. And let me start playing. Well, first of all, a quick overview of linear equation. My dear friends, we all know that an equation in which the highest power of a variable is 1 is called a linear equation. It can have many variables, and a linear equation with two variables is ax plus by plus c is equal to 0. A linear equation of two variables when plotted on a graph gives us a straight line, and we all know that the equation of a straight line is y is equal to c plus mx. Where x and y are the two variables, c is the y-intercept, which is the value of y when x is 0, and this m is the slope that tells us two things. The positive or negative relationship between the two variables and how closely related they are. Let me run this code. Let's understand visually how a linear equation of two variables maps to a straight line. So this is a linear equation, 2x minus y is equal to minus 4, which can be written as y is equal to 4 plus 2x. We need just 2 points to draw a line. So let me put x is equal to 0, and we will get y as 4, and let me put x is equal to 5, and we will get y as 14. So I have 2 points, so I can plot it, and I've used the plot method of the matplotlib. So this is the line. Fine. If you see this graph along the x-axis, for 1 I have the corresponding y value of 6. For 2 I have the corresponding y value of 8, and so on. Each point on this line corresponds to a solution of this equation. So this equation y is equal to 4 plus 2x has infinite many solutions. For example, 0, 4, 1, 6, 2, 8, 3, 10, 4, 12. These all are the solutions to this equation. Note the y-intercept is 4, which means that if x is equal to 0, the line crosses the y-axis 4 units above 0. And this line is rising. That means the slope is positive. So there exists a positive relationship between these two variables x and y. By positive relationship, I mean that when x increases, y also increases. And since the slope of the equation is 2, that means for every unit increase of x, y increased twice as much. Note that when x is equal to 2, y is 8, and when x increases by 1 unit, that is 3, y increases by 2 units, and that is 10. My dear friends, this is the line plot of this y is equal to 4 plus 2x equation. And let me change the y-intercept without changing the slope. Let me change the y-intercept without changing the slope. So this was the equation y is equal to 4 plus 2x, which is plotted over here. And now I am changing the y-intercept to 9, and I'm changing the y-intercept to minus 2. And I'm plotting these three lines now in this piece of code. And since the slope is same, that is 2, but the y-intercept are different, so we have three parallel lines. That is great. Let me now draw the plot of these three equations, and over here we have the same of y-intercept, but the slopes are different. This first equation having a slope of 2, then a slope of 0, and then a slope of minus 2. And this is what I have written over here in this code. Let me execute it, and you see these three lines. Well, this green line represents the equation y is equal to 4 plus 2x. Yes, by 1. 4 plus 2x. Having a positive slope, showing the positive relationship between the two variables x and y. And this purple line represents the equation y2 is equal to 4 plus 0x, having a slope of 0, showing no relationship between the two variables x and y. And you can visually see this, whatever is the value of x, the value of y is same. X is 1, y is 4, x is 2, y is 4, x is 3, y is 4. That means this variable x has no impact on y. And finally, this red line represents the equation this y3 is equal to 4 minus 2x, having a negative slope, thus showing negative relationship between the two variables. Note that when x is equal to 1, this y is 2, and when x increases to 2, the y decreases to 0. Great. Let's see another example over here. So this is an example. Suppose you want to rent a car company to rent a car for few hours. The company representative told you that the base payment that you have to give is rupees 5,000, and then for every hour you have to pay rupees 2,000 additional price. So this is the linear equation that represents this scenario. So this 5,000 is the base value, and this 2,000 is for every hour. So if you have rented a car for let's suppose 5 hours, so this 2,000 will be multiplied by 5. So this is the equation. So y is the dependent or the outcome or the response variable, which is the actually the rent price, and this value 5,000 is the minimum or the base value. This x is actually the independent or the feature or the predictor variable. This is time, and this value 2000 is the coefficient of x, which is the slope. So if I write down this equation and plot it over here, so you get this. So now you can easily get out that if you get the car for 4 hours, you need to pay something about 12.5, a little more than 12.5 thousands, and for 0 hours you need to give 5,000. So this is what this is. So this is graphical representation of this linear equation, and this is another example. This is the linear equation y is equal to 20 plus 5, relationship between years of education a person has achieved and the salary in thousands per month. So this shows that y is the dependent variable, that is the salary in thousand. This value 20 means 20,000, which is the minimum or the base salary. and this x is the feature or the independent variable, that is the education in years. The more education you have got, the more is your salary. And this 5 means 5k, which is the coefficient of x, that is the slope. So the more education years you have put in, the more is your salary. So let me graph this. So once again, you see there is a positive relationship between the education in years and the salary in thousands. So if you have 5 years of education, your salary is a little over 45,000, I think. And let's suppose that if you have 20 years of education or experience, your salary is 120,000. So positive relationship, great. Well, this is another equation. Let's suppose that this is the equation which gives you the relationship between two variables, the drug dosage and forgetfulness level of a patient. Y is the dependent variable, that is the forgetfulness level of a patient. X is the independent variable, that is the drug dosage. This value of 10 is the forgetfulness level if no drug is given, and this 1.5 is the slope. So if I plot this, you see we get a negative relationship. By this negative relationship, I mean the more drug is administered to the patient, the less is the forgetfulness level. If the drug is, let's suppose the is given to the patient is 1 ml, the forgetfulness level is around 8, and if the drug is, let's suppose, 3 ml, the forgetfulness level reduces to around 5. So with this negative slope, you can make out that there exists a negative relationship between the drug dosage, that is this variable, and this forgetfulness level. So these were just the ideas. I think you have a fair idea what a linear equation is and how we can map two variables on a linear equation and how we can graph it. Now the next thing is, what is a system of linear equation? My dear students, a system of linear equations consists of two or more linear equations that you deal with together at once. An example of linear equations having two variables and two equations is shown over here. 2x plus 5y is equal to 1, 3x minus 5 is equal to 2. And this is another system of linear equation having three variables and three equations. Well, my dear students, given a system of linear equation, you can have a unique solution, you can have infinite solution, and you can have no solution at all. Let me describe these scenarios one by one using examples. And before that, a basic recap, or a quick recap of how you can solve a system of linear equation, and this we have done in our secondary schools as well, and that is using the substitution method, elimination method, and the graphing method. And of course, you have done it using the linear algebra as well. However, using the substitution method, if you consider these two equations having two variables, you can easily substitute the value of y from this equation 1 in equation 2 to get the value of x, which we can later put in equation 1 to get the value of y. So this is substitution strategy. On the contrary, in elimination strategy, we add or subtract the two equations to eliminate variables. And before doing that, we may need to multiply one or both equations with some scalar values. And of course, using the graphing strategy, we draw the lines for the equations having two variables, and in case of equations having three variables, we draw appropriate planes. If there is a single point of intersection, that is the solution. So let's see this practically. Please do this substitution and elimination strategy at your own, and let me do the graphing strategy. Let's suppose we have these two equations, y is equal to 1 plus 2x and y is equal to 3 minus 1 over 2x, and let me plot their graph. So this is a graph, and you see these two lines intersect at this point. So this point is 0.8 and 2.6. So 0.8 and 2.6. This is the solution of this system of linear equation. That is, if you put x is equal to 0.8 and y is equal to 2.6, both these equations will be satisfied. Let's see another example, and let me execute the code of this cell. My difference, since over here you see the slope is same in both the equations, that is 2. So the two lines are parallel. That means there is no solution. No solution exists to this system of linear equation because these two lines do not intersect. And finally, let me execute the code of this cell. Over here, if you see these two equations, that is y is equal to 1 plus 2x and 4x minus 2y plus 2 is equal to 0. If we multiply the first equation by 2, we get the second equation. If we multiply this equation by 2, we get this equation. So these are actually the same equation. So if they are same equation, we get the same line. And if we get the same line, we have infinite number of solutions to this system of linear equations. Okay, for better understanding, let us consider a real life scenario. Let's suppose that there is a robber who robbed a bank and escaped in a car with a speed of 150 kilometers per hour. The sheriff starts following the robber after 5 minutes in a car with speed of 180 kilometers per hour. So these are the two equations. The bank robber equation is d is equal to 150t, where d is the distance traveled, 150 is the speed of the car, and t is the time. And the sheriff equation is d is equal to 180 into t minus 5, because the speed is 180 kilometers per hour, and he has left the bank after 5 minutes. The robber leaves the bank. So let me plot these two lines over here. From these two lines, it is apparent that this is the red line which shows the sheriff, and the sheriff got the robber after about 30 minutes, and when they have traveled around 70 kilometers. So this is what the solution of this set of linear equation. I hope this makes sense. And let me replot the line. If the speed of the sheriff's car and the robber car is same, if the speed of both the cars is same, then we have parallel lines. So the robber line is this, the sheriff line is this, started after 5 minutes, and will never be able to catch the robber. And let me do it something like this. If the speed of sheriff's car and robber's car is same and they leave at the same time, then we have infinite many solutions. The sheriff can catch the robber anytime, over here, over here, over here, and so on. Great. Fine. My dear friends, let me sum up what we have learned so far in this section. In case of system of two linear equations having two variables, these are the three possibilities. These are the three possible scenarios. The system of linear equations can be inconsistent or consistent. If there is no solution, we call the system as inconsistent system of linear equations. Note the equations have the same slope but different y-intercepts. If you draw the lines, they will be parallel, so no solution. And if there is one or infinite solutions, we call such a system of linear equation as consistent system of linear equations. If the two equations are independent, we get a unique solution. This is the example. We get a unique solution. And the system is called as consistent independent system. On the contrary, if the two equations are dependent, means the two equations refer to the same line, then we get an infinite solution. If you observe the equations over here, they have same slope and same y-intercept. And such a system of linear equation is called a consistent dependent system. So once we have an idea about system of linear equations having two variables, let's talk about three variables. My dear students, the way a linear equation with two variables is graphically represented by a straight line. Similarly, a linear equation with three variables, when plotted in a 3D coordinate system, is graphically represented as a plane. Well, consider this linear equation: 4x minus 3y plus 6z is equal to 24. To calculate its x-intercept, you put both y and z is equal to 0 and you get 6, 0, 0. Similarly, to get the y-intercept, you put the x and y values 0, so you get 0, minus 8, 0, and for the z-intercept, you get 0, 0, 4. And these are the 3 points. The x-intercept, which is 6, 0, 0, the y-intercept, which is 0, minus 8, 0, the z-intercept, which is 0, 0, 4. If you connect these 3 points, you get a plane, a surface representing this particular equation. Since there are infinite 3D points that lie on this plane, so this linear equation has infinite many solutions. Okay, so now you have a fair idea of a linear equation having three variables and how it can be plotted. Let's see how we can solve the set of three linear equations with three variables. The question is how to solve a set of three linear equations having three variables. My dear students, you can do that using the already discussed techniques, that is elimination and substitution. Graphing them needs a bit of more effort in Matplotlib. So I have not done that. But let me try describing this with the help of some of the images that I have taken from the Wikipedia. And first of all, let me talk about consistent independent system of linear equations. Okay, my dear friends, a consistent independent system of linear equations means there exists a unique solution. An example system of equation is shown over here with a unique solution of 4, 1, minus 2. And this is the image that shows the three planes of these three equations: green, blue, and red, each representing one equation. You can visualize it as the corner of your room where the two walls and the floor intersect at exactly one point, that is 4, 1, minus 2. So this one point resides on all these three equations. So if you put x is equal to 4, y is equal to 1, and z is equal to minus 2, all these three equations will be satisfied. So such a system of linear equation is called consistent independent system of linear equation. A consistent dependent system of linear equation means there are infinite solutions. An example of such a system of equation is shown over here. And this image shows the three planes intersect in such a manner that they make a line of intersection instead of a point. And last category is inconsistent system of linear equation. Over here we have no solution. These are the two example system of linear equations. Three equations, three variables. Well, at the extreme right over here, you see all the three planes are parallel, so there is no point of intersection. In the middle image, you see the two planes are parallel and intersect with the third plane, but not with each other. So we don't have a unique solution. And in this left image over here, you see the three planes intersect with each other, making three lines, 1, 2, and this 3. But once again, there is no single point that lies on all the three planes. So once again, no solution. Well, my dear friends, with this background, I think we are well equipped to move ahead and learn other techniques that are normally used to solve a system of linear equations having more than three variables. Please do this practice and let me move ahead. Most systems involve large number of equations and variables, and it is impractical to solve such systems by hand using elimination and substitution technique. To solve system of linear equations efficiently on computers, we represent the linear equations in the form of matrices and vectors. and then apply different techniques on the matrix equation to solve for the unknowns. And some of the very commonly used techniques are Gaussian elimination, Gauss Jordan elimination, Cramer's rule, and matrix inversion. But before proceeding, let us understand as how to represent a system of linear equations in the form of a matrix equation, that is Ax is equal to B. So, system of two linear equations having two unknowns. Let's suppose these are the two equations. We can write them like this. So the coefficients are written over here as a 2 by 2 matrix. These are the unknowns x1, x2, two variables, and these are the output variables b1, b2. And similarly, a system of three linear equations having three unknowns can be represented as in the matrix form like this, where this A matrix is the matrix of coefficient or the scalar values. This x vector is a vector of variables, unknown vectors. We need to compute them. And if this is the B vector, if this B vector is all zeros, we say that the system of linear equation is homogeneous. Otherwise, it is called non-homogeneous. Okay, now a solving set of linear equations using the Gaussian elimination method. Well, Gaussian elimination method is named after a German mathematician, Lord Friedrich Gauss. Well, this is a three-step process. In step 1, we represent the system of linear equations in augmented matrix. An augmented matrix contains all the essential information about the linear system other than the name of the variables. And this is the augmented matrix for a system of three linear equations having three unknowns. So you see this A11, A21, A31, these three coefficients are over here. The name of the variables is not there. We have a straight line over here, and then we have B1, B2, B3. So this is the augmented matrix of this set of linear equations. Well, in step 2, we apply different operations on the augmented matrix in no specific order to convert them into a upper triangular matrix as shown over here. So this is the upper triangular matrix. This is also called the row echelon form. And to do this, we perform different operations like interchange rows, multiply a row by a non-zero constant, add a multiple of a row to another row. So these are the three kinds of operations we do. And once we have the matrix in the row echelon form, we use back substitution to solve for all the unknowns. Great. So let us practically understand this with an example. Once again, I will have a quick recap, as I assume that you have studied it in your undergrad course. Let's suppose these are the system of linear equations, three linear equations, three unknowns. I have converted it into augmented matrix. You see, the coefficients are over here, and 303, this is the output over here. Now we need to convert this into row echelon form by performing triangularization. And the first operation that I have performed is I have done R2 is equal to R2 minus R1. That is, I have subtracted R1 from R2 and I have placed it in R2. So you see the first and the third row is same, and over here I have subtracted this R1 from R2. So 1 minus 1 is 0. 2 minus this 3 minus 2 is, oh sorry, this 2 minus 1 is 1, and 3 minus 1 is 2, and this 0 minus 3 is minus 3. And similarly on this I have performed R3 minus R1. So R3 minus R1. So 1 minus 1 is 0, this 3 minus 1 is 2, this 2 minus 1 is 1, and so on. And then I have multiplied the row R2 with 2 and placed it in R3, and finally I have subtracted R3 from R2 and placed in R3. So this is the matrix now in the row echelon form, where I have the lower triangular matrix as 0. Now we do the back substitution, that is this 3z is equal to minus 6, this 2y plus 4z is equal to minus 6, and this x plus y plus z is equal to 3. So I have written this matrix or augmented matrix or the matrix in row echelon form in this equation. So we get z is equal to -2, and then I do the back substitution to get y is equal to 1 and x is equal to 4. So this is what this Gaussian elimination is. So we uh, get the system of linear equations into augmented matrix form and perform various operations to bring the equation in this triangular form, and then we do the back substitution. My dear friends, please do practice uh, these three problems, and you can verify your answer using this online calculator as well. Anyway, let me move on to the next technique, and that is Gauss Jordan method. Well, Gauss Jordan elimination is a continuation of Gaussian elimination. Its advantage is that it works for non-square matrix as well. This is also a three-step process. In step 1, we represent the system of linear equation as augmented matrix as usual. In step 2, we apply different operations on augmented matrix in no specific order again, and to convert it into a diagonal matrix as shown over here. So this time we have converted into a diagonal matrix, also called the reduced row echelon form. And the step 3 is pretty straightforward. That is, we don't need to do the back substitution as was the case with Gaussian elimination. So this is the technique. I have solved this example using, you can solve it using paper pencil. So these are the system of linear equation, three linear equations having three unknowns. This is the augmented matrix, and these are the various operations that I have performed on the different rows to finally reduce the matrix to this reduced echelon form, and we have the result. Great. Okay, so the third technique is the Cramer's rule. My dear friends, Cramer's rule uses determinants to determine the solution of a system of linear equation. So let's suppose we have once again a system of three linear equations having three unknowns. We convert it into a matrix form like this, and then we compute the determinants. So for the three unknowns x1, x2 and x3, for x1 the value is determinant of x1 over determinant of this matrix and this. So first of all, the d is the determinant of this matrix A, and dx is the determinant of this matrix by replacing this column with b1, b2, b3. So let me repeat again. So this d is very simple. This is the determinant of this matrix, and this dx1 is, you take this matrix A and this column is replaced with b1, b2, b3 as shown over here. And for dy or this dx2, we replace this middle column with b1, b2, b3 as shown over here. And for dz or dx3, we replace this column, the third column, with b1, b2, b3 as shown over here. So I hope this makes sense. Let me do it on a system of linear equation having two unknowns. So this is the determinant of this matrix. dx, we replace this first column 1, 4 with 3, 6. dy, we replace this second column, that is 2, 5 with 3, 6. We find the determinant of all these and we find x and y, and if you put x is equal to -1 and y is equal to 2 in these two equations, these are satisfied. Great. So this is what the Cramer's rule is. Please do the math, do practice, and let me move ahead. And this is also an example using Cramer's rule for three variables. Please do that. Okay, the third technique is solving a system of linear equations using matrix inversion method. Once again, I have taken an example in which there are three equations and three unknowns. These are the matrix equations. This is the matrix of coefficients 3 by 3, 3 by 1 vector of unknown, and this is again 3 by 1 vector. And of course, doing multiplying both sides by the inverse of A, we get this equation. And if I multiply A inverse with A, we get the identity matrix. And once we multiply identity matrix with X, we get X. So X is equal to A inverse B. So we have this vector B. If we can calculate the inverse of this matrix A, we can multiply this with b to get the value of unknowns or these variables. So this is known as a solution of or solving of the linear equation using the matrix inversion method. And this is the practical example of this. A system of linear equation having two linear equation and two unknowns. So this is the matrix shape. So we need to compute the A inverse. You can easily convert this matrix to this shape. -3 and 4 are swapped, and this -5 and this +2, their signs are changed. You compute the determinant, and finally you get x and y as -1 and 4. Please do the math. And in case if you want to do this using the NumPy, you have this method INV. This INV method is used to compute the inverse, and then you multiply this inverse matrix of A with vector B using the dot method, and you get the answer. So let me run it. So this is the matrix A and the vector B. These are the same matrix A and vector B, 4 minus 7. And then I have used the inverse. So this is the inverse of A. You see the inverse 3 over 2 minus 5 over 2. This is 1.5 minus 2.5. And then we have multiplied this inverse of A with this vector B that I have done over here. And this is answer, -1 and 4. And this is answer, -1 and 4. And you can simply use the solve method of the linear algebra and simply pass it the matrix A and B to get the answer. So I hope this is clear to you. That is the solution of a linear equation using matrix inversion method. Remember, the limitation of this method is that this matrix has to be a square matrix, and its determinant must be non-zero. Okay, so this is another example. Please do the math. And this is another example over here. Over here we have three unknowns, three equations. Let me solve it. Please do solve it using paper pencil as well for practice sake. So this is another example having 4 equations and 4 unknowns. Let me execute this code. Great. So let me prove that this matrix inversion method do have its limitation. And the first limitation is the matrix must be non-singular. Over here, if you see this matrix A, this matrix A is square, but it does not have a determinant of non-zero, I think. So if you multiply 9, 5 to 45, and this is also 45, and the determinant is 0. So if you write down the code of this, you will get the error. And similarly, the next is that the matrix must be square. And of course, we know that if this matrix is not square, you cannot compute its inverse, and hence a solution cannot be found. And these are the possible solutions which we will be talking about inshallah ta'ala in our next session. This pseudo inverse, singular value decomposition, Cholesky and QR decomposition. Great. Okay, so my dear students, keeping in mind the number of equations n and the number of unknowns in a system of linear equations, there are 3 possibilities. And the first possibility is that the number of equations is equal to the number of unknowns. And this is what we have been seeing up till now. The other 2 options are that the number of equations is greater than the number of unknowns. And the third is the number of equations is less than the number of unknowns. Let me discuss these 2 scenarios now in more detail. And the first scenario is overdetermined system of linear equation, which has more equations than the number of unknowns. And of course, these can be consistent, having unique solution, or consistent, having infinite solution, or maybe inconsistent, having no solution. So let me first discuss the first example. So this system of linear equation having two variables but three equations is overdetermined because the number of equations is greater than the number of unknowns. And this is a consistent overdetermined system having unique solution. Let me run this, and you see all the three equations are intersecting at one point, and that is 2 and something point and 2 and probably 1, I think. So this is 2 1. And since these equations are linearly independent, so these are the two equations which are linearly independent. If you closely observe these three equations, you can get this third equation if you multiply the second equation by 2 and add it with the first. And since the number of linearly independent equation in this system is 2, which is equal to the number of unknowns, therefore you get a unique solution. Yes, I hope this makes sense. Let me talk about this. This example also has three equations and two unknowns, so this is also an overdetermined system. And if we plot the three corresponding lines, we get a single line. So we get a single line, that is, the system has infinite solution. And if you closely observe these three equations, they are actually same, having same slope and same y-intercept. And finally, these three equations are an example of inconsistent overdetermined system. If we plot them, you see the three lines intersect at three different points. So there is no solution. So this is inconsistent overdetermined solution. I hope the overdetermined solutions or systems are clear to you. Let's talk about the underdetermined system of linear equation as well. And in this scenario, we have the number of equations n is less than the number of unknowns m. In deep learning, many times we come across underdetermined systems where we have thousands of data points and millions of features in the model. And if you see this single equation x plus y is equal to 3 with two unknowns, this is an example of a consistent underdetermined system having infinite solutions. And this next is an example of undetermined system having no solution. So the system is inconsistent. And one more thing to keep in mind is that an underdetermined system cannot have a unique solution. So far, so good. My dear friends, one last thing I want to discuss in today's session is how to estimate the best possible solution for an inconsistent overdetermined system using the least squares method. Great. Excuse me. My dear students, we have already seen that a linear equation is actually a formal way to represent the relationship between two or more variables. To start with, let us restrict ourselves to two variables only. Some example scenarios are shown in this table. For example, the GPA acquired by a student in semester system depends upon the number of hours that he or she has studied daily throughout the semester. Similarly, the price of a house is a dependent variable that depends upon the covered area of the house. And this y is equal to c plus mx is the equation of straight line. And in machine learning, we normally use the symbol beta 0 for the y-intercept and beta 1 for the slope. This beta 0 is actually the minimum value of y. For example, in case of GPA, beta 0 is the minimum GPA that a student will get even when he or she does not study at all. Similarly, this beta 1 is a value that quantifies the effect of study hours on GPA. If beta 1 is positive, that means there exists a positive relationship between the two variables. On the contrary, if beta 1 is negative, that means there exists a negative relationship between the two variables. An example scenario of negative relationship is this forgetfulness level and drug dosage, where the increase in drug dosage decreases the level of forgetfulness. I hope this is making sense to you all now. Now let's see how we can model linear equation in machine learning with m variables, that is more than two variables. My dear students, in real life, the dependent or the response variable depends on more than one variables. Some example scenarios are shown over here in this table. Uh, for example, okay, let's take the example of GPA again. Other than the number of hours studied, the GPA of a student may also depend on the qualification of the instructor and the training aids or the helping aids, or maybe the lab that the instructor has used while teaching. Similarly, other than the covered area of the house, the price of the house may also depend on other features like number of bedrooms, distance from office or children's school, whether it is a park facing house or not, and so on. And another point to note is that some input or predictor variables might have a positive, while other can have a negative impact on the output or response variable. More so, some variables can be quantitative, while some others can be categorical as well. My dear students, the linear equation in such a scenario will take this form as shown over here. And in this equation, once again, we have one dependent or response or output variable that is represented by y. Since we have more input or independent variables, so we denote them by x1, x2, x3, so on to xm. These are also called the feature variables. The model parameters which are actually we want to learn are beta 0, beta 1, beta 2, beta 3, and so on. Beta 0 once again is the base value of y, which is the value when all the features are 0. This beta 1, beta 2, beta 3, and so on to beta m are values that quantify the effect of respective independent variables on the output or dependent variable. Well, the target of our study is to learn these model parameters. My dear students, to understand this process from the very basic, let's start with one dependent and one independent or feature variable. Okay, so fine. A simple linear regression model is a mathematical equation that allows us to predict the output or response or dependent variable from for a given input or predictor or independent variable. By simple, I mean there is one independent or feature variable that is plotted along the x-axis or horizontal axis, and there is one dependent variable which we want to predict, and that is plotted along the vertical axis or the y-axis. And this linear means the relationship between the two variables is described by a straight line. Well, this regression is a technique used to measure the strength, direction, and causality of both linear as well as non-linear relationship between variables. And finally, the method of least squares is a statistical procedure to approximate the solution of an inconsistent overdetermined system by minimizing the sum of the squares of the errors. Okay, so this is all English. Let us now understand what this actually means using this diagram. Suppose we have 1, 2, 3, 4, 5, 6. We have 6 points. These are the 6 data points that a teacher has collected. Each data point consists of 2 values, number of study hours, and the result or GPA. To plot these 6 observations, the teacher has assumed that GPA is a dependent variable, excuse me, which depends on the on the study hours. So the teacher has kept the GPA along the y-axis and the study hours along the x-axis. Now this is an overdetermined system because there are 2 variables, and to plot a line we just need 2 points. While over here we have 6 different points. And moreover, this seems to be an inconsistent system as well, because it appears that there is no straight line that can pass through all these points. So we need to approximate the solution, and for that we are using simple linear regression model, whose mathematical form is this: y is equal to beta naught plus beta 1 x plus epsilon. This is the error value, with beta naught as y-intercept and beta 0 as y-intercept and beta 1 as slope. My dear students, given the 6 data points, these are the 2 unknowns that we need to determine. These are the 2 unknowns that we need to determine. That is the beta 0, the y-intercept, and beta 1, that is the slope. Since there is only one feature or predictor or independent variable, so we use a linear least squares method to calculate beta 1, which is equal to the covariance of xy over variance of x. So this is the formula of computing the slope using covariance. Once we have beta 1, we can substitute this value of beta 1 in this equation and we can compute beta naught as beta naught is equal to mean of y minus beta 1 x bar. My dear students, you might be thinking what a stupid solution is this, as the line, this line is still not passing even through a single data point. But my dear students, remember this is the best fit line, and to prove this we can prove that the sum of scared vertical distances from the observed points to this best fit line or regression line is minimum. So if I calculate the distance of this yellow line and 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 this yellow line, these will be minimum. Only then this will be a best fit line. I think enough of theoretical concepts. Let us do all this in Python for a proof of concept. So this is the scenario. Consider these 7 data points. Each data point consists of 2 values. The x value is the number of study hours and the y value is the corresponding GPA achieved by that particular student. Well, in step 1, we simply plot the 7 observations using the scatter plot. So these are the 1, 2, 3, 4, 5, 6, 7. These are the 7 observations. From the graph, you can observe that if a student study for, let's suppose, 2 hours daily, he or she gets a GPA of 1.6. And if a student studies for, let's suppose, 7 hours daily, the GPA is 4. So there exists a positive relationship. However, we cannot predict the GPA if a student studies for, let's say, 1.5 hours. So what will be the GPA? Okay, so step 2. Let us now write down these 7 data points as 7 linear equations. One linear equation for each data point by plugging the value of x and y in the regression equation. So you see we have these 7 equations. So we have 7 equations but just 2 unknowns, beta 0 and beta 1. Hence this is an overdetermined system of linear equation. I hope this makes sense. Step 3 is that we always write these 7 equations in the matrix form. So these are the 7 equations. We can write them in matrix form, you see. These are the coefficients of the 2 variables. These are the 2 unknowns and this is the output. So this is the matrix A, this is the matrix X and this is the matrix, this is the vector X and this is the vector B. Note that the matrix A is a 7 by 2 matrix of known coefficients. Since this is a non-scalar matrix, so we cannot compute its inverse. This X is a 2 by 1 vector of unknown and this B is a 7 by 1 vector of vector containing the output, that is the GPAs. And we need to solve this system of equation. Well, my dear friends, there can be different ways to solve, but for the time being we solve it using the least square method. And the least square method is shown over here and I have described it above as well. So you can simply compute it using this formula and I have done it over here. So we have found the slope and we have found the y-intercept. You can do the calculation manually like this or you can use the NumPy COV method as shown over here to calculate the variance covariance matrix. And this we have covered in lecture 4.2 when we discussed covariance and regression. And if I execute this cell, you see once again you have got the same slope, that is 0.46 and y-intercept 0.899. Both give the same answer. The slope is positive while the y-intercept is also positive. Great. Now we can easily write the equation. Y is equal to this 0.9. This is the y-intercept roughly and this is a slope, and we have the equation so we can easily plot it. So this is the line. My dear friends, now we have the line, so we can perform the prediction as well. That is, you give me any number of hours that a student has studied. For example, let's suppose 2.5 hours, and I can predict his or her GPA. That will be 2.1. Also, do note the difference between the actual data points and the predicted data points. For example, the one data point is 2 and 1.6. That is, for study hours is equal to 2. The actual GPA is 1.6. But our model or this line gives us a GPA of 1.8. That is an error value or epsilon of 0.2. And this value is quite less than for x is equal to 1. So we can compute all these error values, and that will be our error. Let me do that as well. You can perform the prediction as well. We have done that. And if you want to calculate the error, so this is the last step in which I have shown you as how you can calculate the coefficient of determination or the R squared error, which can be obtained by the sum of squares of errors due to regression divided by the sum of squares of total variability about the mean. I have used these formulas to compute this R squared error, which in this case is 0.9645. So this tells us that 96.4% of the variation in GPA can be explained by the number of hours studied. So this is a good prediction, a good model that we have generated. My dear students, I have given you a few more examples as well for practice. Please do this at your own. You see, I have given the solution as well. So this is another example. And let me move on to the multiple linear regression. Before I close today's session, let's talk about this OLS, ordinary least square method as well. Well, anyway, by multiple, I mean there are more than one feature or independent variables. For example, consider this equation for multiple linear regression, where this y is the dependent or outcome variable. Let's say that this is the GPA of a student once again. These x1, x2, x3, so on to xm are the input or predictor variables like study hours, instructor teaching skill, lab work conducted, and so on. This beta 0 is the minimum value of GPA that a student will get even if he or she doesn't study at all. And all the features are 0. Beta 1, beta 2, beta 3, so on to beta m are the model parameters that we want to learn. And suppose that we have record for n different students. So in that case, this will be a overdetermined system having n equations and let's suppose m variables or m unknowns. So these are the equations, and we can write these equations in the matrix form as well. I hope this is making sense now. Let's do this using a sample data. Well, this time we have 7 observations, each observation specifying 3 data values. The daily study hours, the instructor teaching skills, and GPA. So this is the daily study hour, that is 1. This is the teaching skill of the instructor. The study hours range from 0 to 7. The teaching skills range from 0 to 4, while the output, that is GPA, range from 0 to 4. And of course, we can write these 7 points in form of equations like this. So we have 7 equations, just 3 unknowns, overdetermined system. Beta 0 is of course the intercept, beta 1 is the coefficient of study hours, and beta 2 is the coefficient of instructor teaching skills. So I've just kept the 2 input variables. So we can write it as an equation as well. So just note that we have the vector now containing 3 values, beta 0, beta 1, and beta 2. And let's solve this system of linear equation. So this time we have the input variables x, we have a matrix. The first column is the study hours, and the second column is the skill set of the teacher. And this is the vector, that is the output, that is GPA. So great. My dear students, over here this time I have used the linear regression method of the scikit-learn library. We'll talk about this in detail in our machine learning module, inshallah. For the time being, just review the code. First of all, just to initiate a linear regression model, we have used the linear regression method, which uses ordinary least square linear regression, OLS. And on this model, I have used this fit method, to which I have passed the matrix X, which is a 2 by 7 matrix containing the input variables, and the vector Y containing the corresponding outputs, that is GPA. Let me run this code. Great. So we have the intercept, coefficient of study hours, coefficient of instructor teaching skills, and the R-squared errors as well. Great. So we can write the equation like this: y is equal to 1.16, that is the intercept, 0.1398, that is the coefficient of study hours, and 0.402 instructor skill. So this doesn't seem to be a good equation. For the reason being, you can note that the study hours do not have a proper impact value on the GPA. And the instructor skill do have a reasonable value, 0.402, but the study hours is having a very small value. Let me do the prediction for this. Let me do the prediction using this. So if I give a value of 7 and a value of 2, that means a student has studied for 7 hours and the instructor teaching skills are with a level of 2, the GPA is 2.94. Let me reduce this to, let's suppose, 1. Student has studied for 1 hour. However, the teaching skill of the instructor are great. And what if the teaching skills are also bad? So it has reduced. Makes sense. Anyway, my dear students, this values might not be giving us a good result, for the reason being that we just have 7 values and I have just randomly selected them. So if you have actually generated the data or collected the data properly, it might have given you better results. Anyway, so yes, I do have another example as well, and that reads the data from a CSV file related to stock price. Please do go through with this example for better understanding of multiple linear regression. And I think that is all for today's session. Okay, so my dear friends, that is all for today's session. We will inshallah continue our journey for this linear algebra for machine learning in our part 2 in our next session, inshallah. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.